Good morning, ladies and gentlemen. This is the very good opportunity, a pleasure also to me to talk to you. This lecture will be devoted to those students who are not very much familiar with the operation of the lasers, and rather to speak, it is an introductory talk. So it will also partly mention some special topics, different branches of sciences, but the major goal is to get some introduction, and I stress again, introduction to the principle and operation of lasers, and what kind of properties of the laser light can be mentioned. So this will be the focus of this talk. It can be framed in a way what is unique in laser light, how can we make distinction between laser light and, say, thermal light sources, other sources, what kind of method do we have to make some distinction between thermal light sources and laser light. I will talk about three topics. First, I will just very briefly mention the basic properties of laser light. This is mainly, should be known to you. If not, then I will make a very rough sketch about it. And the second part will focus, this will be the central part of the talk, it focuses on the coherence of light sources, especially in this case, the laser light, because this could be a major issue based on which you can make a fine distinction between thermal light sources and laser light sources. And to the third point, just to close it, what kind of application can be found in the field of biophysics, because my major field is biophysics, more especially the photosynthesis, how the light can be captured and utilized for useful chemical work, for example in leaves of plants or in bacteria, in some smaller size. These are the major issues which I'm interested in. Just before the start of this talk, I will mention and I will urge you to put questions if you have some troubles. So please do not sit silently in your seat and pass over those things, definitions, themes which are not very interesting, not very known to you. This lecture serves to digest the major issues, properties of the laser light. So I will ask you to put questions, if you have any, and I hope that you have any, or some questions, and do not hesitate to put immediately if you do not understand something or if something is not clear on the figures I will demonstrate to you. If you miss it, then you will miss the whole thing. So then, after the lecture, of course you can put questions, but these are already not so fresh than those who put those questions which arose during the lecture. Now, the first thing, what are the principles of operation of laser? This is more or less known to you. I will just mention a couple of important topics. For example, the spontaneous and simulated emission and absorption, the population inversion. This means that the number of ground state and excited state atoms or molecules depend on which are in the focus of our talk, is deviating significantly from the distribution attributed to Boltzmann distribution. Optical gain, if the system system or state, then a light beam which passes through the medium will not attenuated, absorbed, but just oppositely, the intensity will be gained. The whole system is set in an oscillator. This is called a laser oscillator. It is not a very well-defined system, because if you consider a spontaneous superradiation, then practically no oscillator should be required to operate the system. The laser can operate in continuous and in fast operation. I will talk about some nonlinear effects. For example, let's think of the frequency doubling. It should be very well known to you. What kind of modulators are in a cavity? Two basic modulators, the Q switch and focus cells, should be mentioned. In this case, very important property of the laser is the tuning of the laser. So by different methods, we can change practically the color of the laser light. This can be considered or mentioned as tuning of the laser. The laser types, it's also well known. The active material can be solid state, can be semiconductor, gas, dyes, or solutions. I will stress the importance of the semiconductor. Nowadays, the majority of the laser systems which are in practice are not solid-state lasers, not gas lasers, but they are semiconductor lasers, or light-emitting, or laser diodes, shortly to say, in very tremendous amount of semiconductors are placed in different electronic devices, although you do not know about that, but they are there, and these are mainly semiconductor lasers. These are the basic properties of the laser, which the textbooks mentioned at the beginning, namely the monochromatism. This means that how wide is the frequency distribution or wavelength distribution of the laser light. This means that what is the extent of monochromaticity. This can be highly monochromatic, it has just one color, or it has a wider distribution in the frequency range. This means that it has not only just single color, but multiple colors. Spatial and time coherence, this is what I will talk a little bit more about it, and I will not summarize in a rush way, as I do with the others. A small divergence and high intensity, these are routinely mentioned as basic properties of the laser light, but we will see soon that these are not so essential properties, because we can create from thermal light sources such kind of light sources which do possess this type of property that the laser light is usually attributed to. So these are not so strict. Good morning. Good morning. Take a seat.
Sorry, we're late.
Oh, the night was pretty short, not? Okay, take a seat. I have to tell you anything, because I didn't even start the lecture. I just talked about the general things which we already know. And now come to the major question, which stands in the title of the lecture: what is unity in laser light, and how can we make distinction between thermal and laser light sources, and how can we utilize the high coherence of laser light, how can we change photon statistics, and what kind of correlation exists between the coherence and the photon statistics. We will mention two basic photon statistics, Poisson and Bose-Einstein statistics, and how can it be applied, for example, in photon counting processes. This means that we have such a system, for example, in photographic plate or with other type of chemical reaction can be also mentioned, where it is essential how many photons are absorbed within a unit interval of time. It can be, for example, example, imagine easily as in a photographic plate that you need several photons to arrive within a time interval, so coincidence time, to get blackening of the grains of the photographic plate. This is just one example of the photon counter. So a lot of processes act as photon counter. So then we count the photons, 1, 2, 3, and then, for example, the photochemical process can occur. So under such kind of conditions, for that kind of processes, it is very essential what is the statistics of the light radiation, whether it is Poisson, as in the laser light, or it is Bose-Einstein, as in the thermal light sources. We see a couple of examples mentioned also from the field of photosynthesis. Now, let's see this a little bit more detail. This is a general overview of the system of absorption and emission transition, the Einstein coefficients in the most trivial case in the two-level system. So we have only a ground state and the excited states, so no third or other states will be included in the discussion. In these two-state systems, the different processes can occur. As well known, it can be absorption occur. I will just put this adjective to it, induced absorption. Usually it is not done, but in this case I will stress it. This is an induced absorption. And from the excited state, the coefficient is B12, so if from the ground state goes to the, lifts it up to the excited state. And from the excited state, there is two possibilities to deactivate to the ground state. Either it can be emitted in the induced way or a spontaneous way. The spontaneous way is quite trivial. This is everywhere except observed. The coefficient is denoted by A21. And Einstein came to the conclusion, just for theoretical point of view, that also induced emission should occur. But at that time, when he published this type of idea in 1990, it was far from the discovery of the laser light, so this remained for decades only expectation or idea, a hypothesis, and later when the first laser was constructed at the very beginning of the 60s, in 1962, then it was also really proved that such kind of induced emission is really taking place, and it is practically the major source of the laser light. So, because the linear balance, macroscopic reversibility, symmetry exists, and the two coefficients from the induced processes, absorption and emission, should be equal. So B12 equals B21, and in equilibrium with the radiation field, this balance can be written, namely this means the 2,1 is the emission, and this is the absorption. In the equilibrium, these two terms should be equal, where rho mu is the radiation density of the field. In the first approximation, we can put the Planck's expression in it. This sounds like that. And then from the Boltzmann equation, we can write in equilibrium state this equation. And from this equation, we can get the A21, which is the spontaneous emission Einstein coefficient. Here is a very short summary for the differences between the induced and spontaneous emission. There are two basic differences. The second one is the direction and phase dependence of the induced emission compared to the spontaneous emission, where it doesn't have any restriction for direction and phase dependence. And the ratio of the point which we have to deal with is the spread out of the excited state niveaus. They are not just a single niveau, but there is a distribution of broadening of the excited state in that way. They are not equally populated, but they are more dense at the middle point. This is expressed in the form of a Gaussian type expression. And another important point is the Heisenberg uncertainty relationship, which gives you a direct connection between the natural lifetime and the broadening of this excited state. This is the natural broadening coming from the Heisenberg uncertainty principle. This means that the broadening of the excited state cannot be arbitrarily chosen compared to the lifetime of the excited state. They are correlated. If the lifetime is short, because the product should be constant, if the lifetime is short, then the delta E should be large and vice versa. Another point which should be also partly known to you, if not, then I will give you a summary to that. What is the diffraction limit in the divergence and convergence of the laser light, and also how can it be modified by using a single lens with a focal length of f. Consider the directionality. This is a Gaussian type laser profile with a central maximum I max, and it will drop to, according to the Gaussian spatial function, to the zero. And the question is, what is the directionality? So how parallel this laser beam can be considered. With a distinction between low gain and high gain system. In the case of a low gain system, it can be utilized by a Fabry-Perot resonator, parallel feedback mirrors. This system approaches very much to the diffraction limit. The divergence is very close to the diffraction limit. In this case, the angle of divergence is denoted by theta, can be expressed by the wavelength and the spot size of the laser beam, denoted by RO. And this is a very small value. This is called the diffraction limit. In the case of a high gain system, this is generally much larger. The divergence is much larger than the diffraction limit, which is presented here. High gain system, for example, single pass laser, super radiance. The super radiation is perhaps not so well known to you. If you have just a single cuvette, say 1 centimeter thickness, and put a dye in this cuvette, then the walls itself may already the wall of the cell may already resonator to the system, and exciting this system by, for example, a nitrogen laser, a very nice dye laser can be obtained. At the beginning of my career in the 70s, a very good demonstration for the super radiation was the chlorophyll solution. We put chlorophyll from the leaves of the plant. This has a very nice greenish color. It can be done immediately, so within a couple of minutes time in front of the students for the demonstration. So we could extract the chlorophyll from the leaf, put in a 1 centimeter quartz cuvette, and we could illuminate with a nitrogen laser. The nitrogen laser, you have to know, perhaps this is not known to you, this was the laser of poor people, because it could be constructed at home. So practically, it was so easy to construct. It had a 337 nanometer wavelength. This is in the UV spectral range. And if you irradiated this chlorophyll solution by this nitrogen laser, then a very, very nice red light came in both directions out from wall to wall of the lecture hall. So this was a very strong and very colorful demonstrative experiment was it. So this is a super radiance, super radiation, so it didn't need any type of adjustment of the optical part, the resonator, mirror, etc., etc. Nothing was required because at a single pass through the cuvette of chlorophyll solution, the gain was large enough to get a very high intensity chlorophyll laser light. So this is a high gain system which I mentioned. Of course, the divergence was not very, very large, but was not small, so it was far away from the diffraction limit, but practically in this distance from wall to wall of a lecture hall, it seemed to be quite parallel and quite demonstrative. No, examples. Let's see a laser light which has a 500 nanometer wavelength. The spot size will be, say, 5 centimeter, and then in this case the diffraction limit can be calculated. It is roughly 3 microradian. By illuminating the surface of the moon, the distance between the moon and the Earth is so much, so roughly 4 times 10 to 5 kilometer. Then, due to this divergence, it will illuminate an area which has a diameter of roughly 2.4 kilometer, which is not very, very large, illuminating from the Earth. The second example I mentioned here, the Apollo 11, which placed a corner cube reflector on the moon surface to measure exactly the distance between the Earth and the moon. This is roughly the delay was measured, is roughly 1 nanosecond, it corresponds to 30 centimeter, and the round trip was roughly 2.5 seconds. Okay, and let's see what the lens does with this system. Is focusing. It will not focus the lens point, but it has a finer spot size. A smaller spot size can be expressed in that way. This type of curvature in the vicinity of the focal point can be considered as being raised. For example, if we take a converging lens with an f number of 2, then applying the laser light of 600 nanometer. What color is 600 nanometer? Not to see, not to fall asleep. This is why I'm asking you. If you do not ask me, then I will ask you. 600 nanometer, what color is it? Blue. Maybe you have a very special eye. Could be. I do not have your eyes, but then I can. But in a normal day, 600 nanometer, what color is it?
600?
Yeah, no, 600. What color is it? This is just a question. A very short question. Unpleasant question in that way. Yellow. Yellow is so what is the color of the sun?
Well,
that's yellow, not?
No, it's like multiple, like if you want.
Yeah, but if you look at the sun, what is the color of the sun?
If you want, you're right.
And blue, what is the color?
White.
White. You mentioned yellow. Is it not yellow? Maybe we have different feeling senses of colors. We have different eyes.
500 is green.
500.
400, 500
Yeah.
green, and 800 is red.
And what is for example, if you have sodium lamps? Did you see what is sodium emission or sodium lamps? Did you see? Never. For example, the streets illuminated earlier with this sodium lamps, or even in Netherlands, for example, the eye rays. Now it's not so fashionable because of the of the light in the night, and then you disturb the birds, etc., etc. So the environmentalist fights against the lighting of the high street in the night. It's enough for the cars if they illuminate the place. So what is the color of the sodium lamps?
White.
White.
6,000
How much? 550 nanometer. That's if you put the sodium in the flame, the Bunsen flame, and what will be the color?
Yes.
This is yellow. This is yellow as the sun, where the emission maximum is. You are right that the sun is white because it contains every wavelengths, but the distributions are not equal. So it has a maximum around 550 nanometer. This is why we see the sun normally as yellow in color.
Yeah.
Okay, 550 yellow. 600, nobody knows. Red. Red. Coming from the East European countries, not? Yeah. From the communist countries. Yes, so we are invading with this color. Red color, everything was red. Not only the blood, but even our idea was painted by that. The stars, etc. Always red. So 600 nanometer, it starts to be already red. 580, very close to 600. What kind of color is it? You are sitting on the first row. This is why I'm asking you. This is a drawback coming late, not? This is a drawback. If you come late, you have to take a seat in the first row. And you will be exposed to the danger that I will ask you. If you were also late, but in the last line, that was a very smart choice, very smart. Because I do not ask you what is the color of 580 nanometer.
Orange.
Orange. Excellent. Orange. Excellent, excellent. I mentioned you the nitrogen laser. It has a wavelength 337 nanometer. Should I put it down? 337 nanometer. This is nitrogen laser. Emission wavelength. What color is it? So I will suggest you to take the last row in the next lecture. Okay? This is ultraviolet. That's excellent. Ultraviolet. Do we see this laser? No, we don't see it. Yes, we do. What color is it? So of course not directly in the eye because this will be dangerous, but from scattering. What is the color of the laser light 337, which is the UV? We shouldn't see it, not, but we do see it. For example, if you should like to adjust the light path of a nitrogen laser, how can you do that? You will have a small piece of paper, and then you will see where is the light. Okay? And of course the nitrogen laser is continuously working in pathway, and you can see and you can adjust the optics, whatever you wish. So we do see this light, 337, and because you do not have any experience of that, I will tell you, this is bluish light. So what would be my next lecture? Why it is blue? Not? Why is it blue? If we shouldn't see the UV light. At least, do you feel this contradiction, my lady? Do you feel this contradiction? What is this contradiction? So we shouldn't see the UV light, and still we see it in blue. This is a contradiction. How can you solve it? Nobody.
Maybe because
Sorry?
maybe because it's near 400 and we can
Yes, it's close to 400, but close, but no cigar. So normally you don't see it. This is although close to the bluish part, 400. I agree with you, but close, but not there. There's definitely what is the 663 nanometer difference. That's pretty large, not? So we shouldn't see it, but we see it. Why? Of course, if I tell it, repeat it once, twice, 3 times, it will not help you to give the answer. No, that the answer for that is, at least for I will interpret in that way. This shouldn't be the exactly the right answer. Maybe somebody else will figure out another explanation. Maybe you will figure out after the lecture when you will relax already and also exhausted us right now. So they're coming after the breakfast to run to here and sit down. You can take some breath. And then after 1.5 hours, you can relax and you can think smart about this idea. And you will give me another explanation, as I will do right now. So this UV light comes in your eye. The glass lens, for example, which is the majority of the eye, is constituted. And it with this UV light will excite the ingredients of your eye. For example, the glass body of your eye. And it will emit fluorescence. This is not the same light as was excited. This is the nitrogen laser 337 nanometer. But what we see is the fluorescence light excited by the laser light. It's clear. So this means that if you want to make a bad picture, then, for example, here comes the UV light, 337 nanometer. It comes to here, excites the glass, the body glass, and this will make fluorescence. And this is the fluorescence what you will observe in the retina. It's clear? Could be clear. I don't say that this is the only explanation for that, why we see the UV light, it's a bluish one, but it's a rather common phenomenon. If you have a UV light source, you have to be very careful not to excite fluorescence. And everything will be excited by the UV laser light and will emit fluorescence, for example, in the blue part of the spectrum. Okay. So much for today, for the colors. So the 600 nanometer is a red laser light, and for example, if we try to focus, then the smallest spot size, of course, is not 0, but it will be focused the spot size of 1.5 micrometer, which is the size of a cell, for example. So with the normal collecting converging lens, we can very much collect all the light in the size of a cell, roughly 1 to 2 micrometer. Now, another, the time is running, but I'm also running right now. The increase of the laser light. You will visit here a couple of labs in Szeged where high intensity lasers are operating. This is just in the Hill Labs, for example. This is just a very short sketch how the intensity of the laser light increased during the time in the last half century. This was the invention, discovery of the laser light, and then by using the first boost switching and mode locking, the intensity of the laser light in the middle of the 60s could be significantly increased. Then nothing, practically not major increase can be observed for at least 1.5 decades. And in the middle of the 80s, they could amplify the chirp passes, and then a new area appeared by increasing of the light intensity. In this range, this was not very unexpected, and not much novelty could be brought out because the bound electron's energy was in that range. But if the energy increased, or the energy of the laser increased this level, then the electrons could be escaped, and the laser could be evoke free energy, free electrons, and then they can interact with each other. The limiting area or energy range is 10 to 21 watt/second centimeter quadrat, where the relativistic optics starts. This means the electrons will have so much energy that the speed can approach the speed of the light in vacuum. And then from this, above this threshold, new phenomena occur. I do not tell about it, the zeta watt lasers. In this range, the light beams will interact with each other. If, for example, two light beams will cross each other, then due to the interaction and that very high energy range, they will deviate the opponent light beam, and the interaction will be quite straightforward. Non-linear effects will occur here, and the details can be asked when you visit these labs next week. The high energy, high power, intensity, and brightness, this is usually the characteristic of a laser light. Here is the power, the energy, etc., which is important for us to make some examples and to make calculations in order to see it a little bit closer than usual. One example is mentioned here where we compare the brightness of the sun with that of the typical helium-neon gas laser. The helium gas laser, this was from 1963. This is the most common laser light source with a wavelength of, it's not here, 632 nanometer. What is the color? 632 nanometer. This is red, definitely red. Yes, you are right. So we have a red helium-neon gas laser. The sun's surface temperature is roughly 6,000 Kelvin. The power density of radiation can be derived from the Stefan Boltzmann law, and then we can calculate the brightness of the sun is the power density unit of solid angle. The total solid angle is 4 pi, so the total solid angle, and the brightness, practically the power density is divided by this solid angle, then you will get these numerical values. If you calculate the brightness of the helium-neon laser, the spot size is roughly 1 millimeter, the power is say 1 milliwatt, usually the divergence is half a milliradian. Then we can calculate the power density, the solid angle, and then we can finally will get this value. If the brightness of the helium-neon gas laser is compared to that of the sun, then we will get that in this special case 300 times larger brightness of the helium gas laser will be obtained than that of the sun. The next example considers a comparison between the light bulb and laser light. We will let light coming from the light bulb, from tungsten lamp, for example, from laser light, and we will compare the situations. The light bulb has 20 watts. This is a very, very timid, flaky light bulb. It's hard to see. It can be used for illumination of a larger area. Let's consider 20 watts from a distance of 5 meters, and the question is what will be the intensity on the retina. In this case, it's roughly 10 to 6 watts over a meter square. If you consider it with a laser, which has 2 milliwatt radiation, then you will get larger excitation, which is has two problems. First is here the focal point and over the line is very large. Second is it contains ultraviolet radiations, and these two factors together will prohibit to look directly at the laser. Second point. This is the largest part of the lecture. What is the coherence, what are the basics, and what are the applications? So we will focus on one property of the light. This is the coherence. What is it? Why is it important? The light sources can be divided roughly into two parts. The thermal light sources, which mainly come from the sun, or flash lamps, or tungsten filament, or a welding guard. These are all thermal light sources. Another category of light sources are the lasers. The different demonstrations of the lasers can be seen. So these are the properties which were mentioned: the directionality, the small pot size, high energy, power, intensity, brightness, monochromaticity, coherence, photon distribution. What are the major property which